Thank you very much, Paul. I mean, this is that I could not do what I wanted to do. I just told before because I wanted to go to Zeidlinger's group because I wanted to do correlated photons. There was no space left, so I had to go for the atoms. And I was a little bit bored by the atoms, so single particle physics, interferences, and so on. Then I wanted to go to Oxford, doing their BEC now for the first time, doing many particle physics, doing solitons. And even there they said, well, you know, an expert in matter wave fields, and so you should actually do this interferometry experiment. And then I went to Constance and started my own group as a young researcher, and there I made a proposal about squeezing of matter waves. Okay, that was 2000, this proposal. And it was about solitons, using solitons for squeezing. And essentially, this is the wrong approach. We did squeezing 8 years later in a very different way, and that's what I'm going to tell you now. And so now, as you say, I can do what I want, but somehow we're still stuck with the things I wanted to do as a PhD student, namely doing correlated particles and seeing if I can see entanglement and use entanglement for something. Okay, and that brings me to the topic of today. And I will talk about quantum metrology with Bose Einstein condensates. This is something, quantum metrology is the way of doing measurements better than classical possible by using correlated states, quantum correlated states. And you can use different platforms for producing them. And we have the platform of Bose Einstein condensates. And for doing really precise measurements, like for time standards, standard minus 18 level, this might be not the best way. But it shows you kind of roots, how to produce entanglement and how to use entanglement. And so I will start with a very general introduction, a very basic introduction about quantum metrology. And then I will give two examples. One is the easiest way of doing better measurements is taking Gaussian states, which are actually relatively classical, but it takes squeeze states. They have variances reduced in the direction you want to measure, and with that you can do better measurements. And there's entanglement in there. But more interesting is to go to non-Gaussian states because they should actually have more resources than squeeze states. The best case state you can have is a noon state, N0, 0n, which has the maximum performance in metrology, namely 1 over n scaling of the error. And I will talk about these states, how we produce them. But then actually, if you have non-Gaussian states, how to classify them is not so easy anymore. If you have Gaussian states, it's simple. Gaussian is defined by the mean and the variance, and all higher moments are given. But for non-Gaussian states, you have to ask, what do you have to measure? And that brings us naturally to quantum Fisher information as a tool for showing the resources in these states. And this is I will do this in a very experimental way of explaining it because it's kind of instrumental defined as I do it. And that makes it nice because it's theory independent, which I, as an experimentist, like. And then at the end, I will just touch on that. The latest results we have is that we can do quantum enhanced sensing via time reversal of nonlinear dynamics. And that's a little bit in the direction of, if you can generate entanglement, very often you have lots of entanglement in your systems, but you cannot use it, you cannot address it, you cannot access it. And one way of accessing it is if you can time reverse your dynamics, then you can use it directly. This is another problem, how to do time reversal experimentally, but we have a system that we can do that, and we showed with that you can do Heisenberg limited detection with 4 particles, which sounds not so interesting because 4 is not a big number. But the interesting aspect of that is that the detector had a noise of plus minus 4. And this only thing worked because we used nonlinear dynamics in reverse, and I'm just touching on that at the very end. Okay, so quantum metrology. It's always nice to have a paper you can put up which explains what quantum metrology is. And there's a paper 2006 with the title Quantum Metrology. And this is worth reading, and I had to read it many times in order to appreciate the paper. And so what they discuss is here a very general basis. You have some resources. We call this here channels. You have transformations. They're all the same on these channels. And you have a detector. And the basic question is, given the measurements here, how well can you estimate the phase phi here, or this parameter phi? It doesn't have to be a phase. In our case, it will be a phase of an interferometer. Okay, now this is the classical. And it's CC, classical, because classical input, classical output. Now the first thing you can think of, well, if I can entangle these outputs, can I do a better readout here, or actually from the readout here, can I better estimate this parameter phi than here? And the answer is no. That's interesting. So if you have your measurement device and you entangle afterwards, do a better readout, so to speak, it does not help you. You need the resource while you do these transformations. You need the entanglement while you do the transformations. So the other two sequences are better off than classical. If you entangle first your channels, do the transformation and measure, or do entangling, and then I will call this, in our case, it is disentangling the system, you can do also better. Okay? So the name of the game is, this part here is the classical part. You cannot do better than 1 over square root n, the shot noise limit, as you may know, from independent measurements. Well, here you're actually bound not by square root n, by 1 over n. This is the Heisenberg limit. Mm-hmm.
You assume that this operation is linear.
Yes.
So this
yes.
includes this
No.
anybody.
No. It's a linear operation, single particle operation. And you want to estimate this parameter phi, or this parameter. Yeah.
And this is a statement that after many body we do some entanglement. Does it apply also to that case or no?
What again?
So if the operation was nonlinear.
Yes. So yeah. Then it's a question of what do you define as your operation. Yeah. If you start to have a nonlinear operation here, which does depend itself on n, right? Then you would get a better scaling even in this case, right? And I don't want to use this now here. So here, this is the definition of single particle operations of each of the particles operating individually, and then from that you ask what's the estimation. Okay. Otherwise, you play a game of making a phase dependent on n. Yeah. And so this is not what we're going to talk about here. Okay. So to be more specific to this kind of unitary transformations, we are going to do interferometry, and this is very straightforward. So you have particles coming in here, you have two paths, and you have a readout. The readout is the particle number difference here in the output, and you get, for one realization, you will get one number of particle number difference. But we all know what happens if you change the phase here. What we get is that the particle number difference will develop a fringe, and i.e., as a function of phase difference, or phase here, phi, you will expect a different value of particle number difference. But as you see, this is one result. You cannot tell much about one result. You have to repeat the experiment over again, and then you will see that you have statistics. And at the end of the day, you will get a certain distribution of particle number differences. And now you ask, how well can I estimate from this distribution the phase phi? That's what you want to do. And if you have this linear combination here, or this linear relation between signal and parameter, then you would say, well, this is very straightforward. Error propagation, i.e., the uncertainty in phase is directly connected to this variance via this slope. Okay, so now if you do the input in those arms, both arms, then essentially not much change beside the phase changes here. But additionally, you have now the chance to correlate the particles, the input particles from both boards. Okay, you entangle them. And now the first thing you would do is, and what is discussed in this context is squeezing, namely you make the correlation such that the noise is reduced in the output. And so at the end of the day, this gets a smaller distribution here in noise, and then with that you would say you can immediately estimate better the phase phi. That's the squeeze state. How to produce that is actually the name of the game. You have to make correlation between the particles, and I'm going to explain that. But this is now, for quantum metrology, the simplest, the first approximation. More generally, metrology is about parameter estimation. So essentially, you have this device, you have two phases, phi and phi prime, and you want to know if you can distinguish phi from phi prime. Now, this can be an arbitrary signal, and what you have actually is not a function of the thing you want to measure and the signal, but what you have is conditional probability distributions, i.e., given the phase phi, you have a certain distribution of the signal. Okay, this is now classical. We can measure that. And if we would do this now for the case we had before, we would see, well, the conditional probability distribution for a phi prime looks like this, and these two Gaussians are distinguishable, and we say, now I can distinguish the two phases, and that's my resolution. Okay? Now this is very general, what I wrote here, because these distribution functions don't have to look like Gaussians. They can look arbitrary. Okay? If they look arbitrary, for example, like this, then you would say, well, how can I distinguish this from that? It's not the variance which is a good measure anymore, because you have this hump in between, which you might use for distinguishing the two functions. Okay? Now, this is a general problem, a classical problem discussed in the 20s of last century. Given you have these conditional probability distributions of phi, how can I estimate from a measurement set the phase phi? And what's the error on it? And that's given by the Kramer-Rao bound, which says the error you can do with this, given these functions, is the error on the estimation will be 1 over square root f, where f is the Fisher information, which you can calculate from the distribution functions you have. Okay? Now you have to take what you see here, what enters is how does the distribution function change as you change the parameter phi, okay, weighted by the conditional probability distribution function. So essentially a little bit what's in there is how sensitive is the distribution function as you change your parameter. Does it change fast or slow? And at the end of the day, what we are going to do is we were going to measure the distance of the distribution functions. So the distance measures for functions. You can use that and show that quantum mechanically the distance increases faster than classical possible. That will bring us how we measure the Fisher information. Now, this is a classical description. Now the question is, what is f? Is it limited? Can it be arbitrary? And this is this paper, again, in this paper they discussed that essentially for all separable states, the Fisher information, and they don't use Fisher information in the paper, but essentially their statements can be summarized like this, that the Fisher information for separable states is always smaller than n, and for entangled input states, it can be as large as n squared. Okay? Now if you plug n squared in here, you see 1 over n scaling for the error estimation. Now, the question now is, these states having this property are on your side because you can do better measurements given the same resource, i.e. number of particles. Okay? Now, it might well be that you can induce them because given the n squared scaling here, it's the maximum fluctuating state. It's another statement in this paper. If you want to get good phase sensitivity, you would like to have in the interferometer maximum fluctuating state, i.e. maximal differences is good. Which sounds a little bit against this squeezing idea. You want to have small fluctuations. But essentially, if you have large fluctuations, these large differences will pick up large phase differences because it goes n times the phase you pick up. The problem is that if you have this state, the distribution functions look like this. Okay? Now, if you go further, you see, if you zoom in here, I mean, there's no variance to it. This makes no sense here. But you have a structure which says, like you have here in one phase, you have only even number differences. And if you change the phase by 1 over n, you have only odd number of differences. So essentially, you have this beautiful entanglement, but you have to have a single particle detector which allows you to measure parity, odd or even. And then you can resolve very well phase differences between 1 over n and epsilon, but you cannot differentiate phase shifts from here to here because they are all the same. They are periodic. Okay, so this is at the end, the final story I'm going to not talk about this too much, but if you have this state, this is hard to read out. But if you can produce this state and run backward the time propagation, you can use, again, your simple detectors using all the resources built into this state. Okay, so now for the following, I'm going to explain you interferometry and squeezing, and I need hand-waving arguments. And for that, I have to introduce something, namely, I'm going to introduce interferometry on the Bloch picture. Okay, so an interferometer is a device which can splits a path into two directions. You can see this as spin up and spin down. This is a general two-state system. The most general superposition you can have is this plus this with arbitrary amplitude and arbitrary relative phase. And these are two numbers, and this you can represent on a sphere and the Bloch sphere. And if you point upwards, this means the particles on the left-hand side. If it points downwards, it's on the right-hand side. And if you have a superposition between spin up and spin down, then you spin in X direction. So a coherent superposition between left and right is a vector in the plane, and the phase of this vector is directly the phase difference between left and right. Okay? So essentially, an interferometer is now a pi over 2 pulse, some phase evolution, and a pi over 2 pulse. Okay? And if you add these angles up, you find out essentially it's a rotation around a certain direction, the y direction, for example. And what you want to measure is actually the rotation angle of this vector. So essentially, interferometry is about, can you detect, what differences of this vector can you detect experimentally? That's the resolution of the phase resolution in your experiment. Okay? So if you have one particle, well, a spin and a half is either up or down. There's not much information in there. That's kind of clear, and that's why you want to have more than one particle. So you can repeat it many, many times and do averaging, or you just take it in parallel, non-interacting particles. And the nice way of this sphere is that you can just somehow add spins up. And if they're uncorrelated, the spins add up to a vector, which has a certain uncertainty because they are randomly orientated. You add them up randomly, and that gives you a distribution here. You can do this mathematically correctly. This is Schwinger collective spin representation by saying, well, this vector here is just a sum of individual vectors. Okay? And this uncertainties here, which I explained by random adding up spin directions, is nothing else but the uncertainty you get from the spin algebra of this angular momentum operator. Okay, so now if you look at this, we have this uncertain vector in this direction, and essentially I said the phase sensitivity is given by how I can distinguish the angle. That means the variance here in this direction is directly connected to the variance I showed you before with the particle number difference, since the z direction of this vector is particle number difference. So up is left and down is right. For many particles, this is how many particles are up minus how many particles are right, or left and right. Okay, so this is actually just the variance, and with that we would now understand also in this picture that the variance of this vector gives you the uncertainty in phase phi. Now if you make it larger and you want to measure more precise, you take more and more particles, then essentially what happens is that this variance here grows with n, okay? But the good thing is the area of the whole sphere grows with n squared, and so you get better and better localized on the total sphere. And that allows you to measure more and more precisely the position. The scaling goes with square root n, and this is exactly what you see here. It just like gets smaller because you normalize to the total signal. So essentially the error, relative error goes down. Now this is a classical limit, and we want to do better, and with this drawing you can do easily better by just squeezing this whole thing. So you make the uncertainty smaller in this direction where you want to measure on the cost of the other direction. And this brings you now to this kind of situation that you have an entangled input state, bi-entangled, but in order to get this ellipse you have to add up the spin in a very special manner. They have to be correlated, add up in a certain way in order to get this kind of ellipse. So in this respect these spins will be entangled. Now how do you reach this? How do you make this particle seeing each other? Okay, there are different routes. One route is take these gases and interact with light. Okay, then you can measure what the spin orientation is, and then if you can do the measurement better than the shot noise of the particles, then you can do conditional squeezing, i.e. the next measurement will be now better than before. This is actually the best squeezing we have so far. It's about 18 dB squeezing in Markiewicz's groups and James Thompson's group. And the other way is also using the back action of light on the atoms in order to produce these correlations. You can do ions, ion trapping. You can have Coulomb interaction, which gives you this kind of interaction. And we are taking direct interaction between the particles by collision. So there's a big group of people working on this demonstration of this atomic squeezing using different techniques. So the first part is using atom-light interaction. They are using collisional interaction as we do, and John Bollinger uses Coulomb interaction essentially in about an ensemble of 80 ions in his spanning trap. Okay, so now for us, we are doing collisions, and I started with do BEC, so this comes for free. But you can also try to find a state which has this shape. And this shape now is a little bit different because you would say, if I look at the variance of this state, this is bigger than the classical one. So the variance, on the variance side, this is not good. But if you look at it, you would say this is a very correlated state. In order to get the spins orientated in this fashion, they have to be correlated in a very peculiar manner. Okay? So there is some entanglement in there. There is some resource in there. And it turns out actually there's more resource in there than in the squeeze state. And that's why I would like to go for these kind of states. And I'm going to show you now how you produce the squeeze states and this question mark state. The system is a standard BEC machine. We use two states, f equals 2 and f equals 1, first order Zeeman insensitive, but second order is non-zero. We can detect the atoms quite well by absorption imaging. So we can, this blob here is one condensate. There are 500 particles in there, and the error on this particle number estimation is ±4, which comes actually from the photon shot noise we are shining on, because a shadow is relative to what comes in and what goes out, and if the income is already noisy, this gives you a noise on the atom number itself. This is ±4 in our case. Now, we want to do this kind of internal degrees of freedom. This is now spin up, spin down, or left and right in the following. We detect these atoms consecutively. So first we detect f equals 2, and then we detect f equals 1. And again, this is one interferometer. This is up and down. That is a little bit more spread, comes from the imaging, but essentially we can detect the particles as well as up here, plus minus 4. Now, I'm going to show you statistical data, i.e. we are going to look for noise, and it means one of these experiments gives you one number. Okay, and now you want to do statistics on this number, and producing this part here takes you 40 seconds. So essentially, having statistics on doing noise and even distribution functions, you would like to have higher throughput. Okay, the first step was this kind of 7 or 6 condensates next to each other produced in one shot. And what we do now is we do 40 in one shot, which essentially turned out to be extremely important for doing systematic. Because most of the experiments are first systematics in order to understand what's going wrong before you can do what I show you at the end.
And these measurements are all strictly of atomic densities alone?
Yes.
They're reducible to density alone?
Yes, yes. But what you can do is you can do unitary transformation beforehand, and with that you can measure any orientation of this collective spin vector. So it's always density measurement. It's particle number counting, but you can do before a unitary transformation. Yeah, and you can rotate the state as you like. Okay, so the system we are using for producing the squeezing is shown here, the 2 internal states, and the Hamiltonian describing the dynamics of this system has been discussed in '98 already by Steele and Collett. And essentially what you have is a linear coupling, i.e. you go from A to B and B to A with a certain coupling constant. This is a 2-photon transition, microwave RF transition, which we can control very well. So we have full control over omega in magnitude as well as in phase. And you have a term which depends on particle number difference. So this is particle number up minus particle number down squared. This is just coming from the interaction energy, since each particle has energy depending on how many particles are around, and the total energy is given how many particles you have, i.e. n squared. Okay? Now this Hamiltonian has many names. You can see this as 2-mode Bose-Hubbard model, quantum dimer, or fully connected transverse field Ising model, Lipkin-Meshkov-Glick Hamiltonian. Now seeing the fully connected transverse field Ising model might be not so straightforward directly if you look at this, because where are the spins here? But I started with arguing about spins. I said A is up, B is down, and I'm talking about collective spins. So if I recast this equation here in my collective spin variables, then, actually I should tell you before something else, but I just do this is not so important. Then what you get is, that get the term which depends on Jz squared, and Jz is a sum over all sigma sets. And if you square this, then you get all products of all spins with each other. So essentially it's a fully connected Ising model, while this one here is a transverse field, right? It just couples, it puts a field on this, and then it starts to precess in this direction, which is Rabi oscillations. So this is, and then you can study what happens with a function of omega compared to the nonlinearity. Now, what I've just skipped over was that this nonlinearity here, essentially for rubidium, is 0. Which is the speciality about rubidium, about the scattering lengths, similar on triplet scattering lengths, and they turn out to be such that they compensate all the interaction terms, so that chi gets 0. But you can use a Feshbach resonance for the specific states we use. We can use a Feshbach resonance to enhance it. With all the caveat that you have losses, and so at the end of the day, it's a balancing how much you can lose, how much you need in order to produce squeezing, that something is surviving at the very end. Now, at the end, what I will show you is that there's an additional term here. I wrote constant, which theory people very often neglect and say, well, it's constant, I can just take an offset of energy, which is right. But it turns out this constant is a constant of this form. There's delta, which is adjusted frequency difference between the coupling. This is indeed a constant. I can adjust this. But then there is this term which goes with n, total number of particles, which is not a constant in the experiment. Because the experiment will start with 300 particles plus minus something. So essentially, the experiment will have the problem if you don't do post-selection, and that's what we had to do at the very end. If you don't do this, then you have a fluctuating term here, n, with Jz. So essentially, you always have a certain field in a set direction, which is randomly pointing in arbitrary directions. Okay? So you can get rid of that by doing post-selection, which we have to do at the end. I will show you. This cost us to understand that this constant term is a problem for us, was about 4 months. Yeah, good. So now we have the Hamiltonian, now we want to do squeezing. Yes?
But that's a very high price to pay. You have to throw away a lot of data.
Yeah, I show you. You know, like there are two sides to it. One side is you want to have 0 here. That's true. Then you have to throw away lots of things. But you say, I don't care. I know this Hamiltonian. I know also what happens with the tuning. So now you can take all numbers you have, and you get automatically the tuning dependence, which is a systematic check, which is maybe helpful. We'll see if it's good or bad. Okay, so we have this Hamiltonian at hand, and now we want to do squeezing. And the first thing is one-axis twisting squeezing, i.e. you get rid of this linear coupling here, and you just let act the nonlinearity. And what does it do? Well, that's actually, you have a Hamiltonian J set squared, so the time evolution is given by this form. And you know the angular momentum operators are generators for rotations. So essentially you can read this like there is a rotation around the z direction where the angle we rotate about depends on J set itself. So that means the higher you go up, the faster it rotates. Okay? So essentially this is the behavior. So if you have something like this, the distributions like this, then this will go to the right and this will go to the left. If it's further up, this goes further to the right and this goes further to the left. So essentially you get a shear. Okay? This is good because what you have now is you have correlations between particle number difference to phase. So you have correlations between number and phase, and this is what squeezing is about. There are correlations between phase and number. Okay? So now how do you do this? Well, the first thing is you start with this kind of nice blob in this direction. How do you do this? Well, this is very simple. You take all particles pointing down, and then do a single particle rotation of each of them. Okay? If you do each of them rotation, then they are independent, and you add them up, you get this coherent state as I showed you before. So you get this blob here by just doing a pi/2 pulse, and then you just switch off and wait. If you wait, then essentially this ellipse will start to shear, and you have squeezing. Now you do the experiment. That looks like what the experiment looks like, so you have to repeat the experiment over and over again. This is now one realization here. This gives you one number, and now you have to do statistics of this number and number differences. And you would say, well, I have a squeeze state, so what should I see here? And what you should see here is from the squeezing not much, because essentially you measure only, as was pointed out, you measure only density. So you measure particle number up and particle number down, and this didn't change. Because you had no exchange of particles, you just were like giving them a phase shift. And the phase shift you cannot see by just detecting densities. So what you have to do is, you have to do an additional transformation to make the phase into particle number difference, because it's the only thing you can measure. But we know how to do this. It's an interferometer, and the interferometer does exactly that. The phase is changed into particle number difference via a beam splitter at the very end. So you do this, you rotate this state around this axis here. You can do this via linear coupling, i.e. microwave and RF, and then you think you are done. The problem is, you have to hit the middle very precisely. If you don't do this, if you rotate once in this direction, one in that direction, one in that direction, then essentially what you do is you average over different rotations, and then the variance will get larger. Right? If you rotate this around this axis, you will turn down the ellipse here, and you measure only the z direction. So essentially you rely on the fact that you have good control of your rotation axis. This is a small problem because we are magnetic sensitive. Not first order, but second order. That gives 10 kilohertz per Gauss, and it gives you a certain stability criterion for your magnetic fields you have. We work at 9.1 Gauss in order to have the Feshbach resonance, but we needed a stability of 100 microgauss in order to do this experiment. And this is actually not so difficult. You just take a flux gate, stabilize your magnetic field actively, and we can get down to below 100 microgauss at 50 hertz. And if you have the stabilization, then you can do these rotations and measure particle number differences and make these nice plots where you show, this is one example, it's not the best case, but it's one typical example, where the variance of particle number difference goes down as you do the rotation angle, and there's a minimum, in this case it's about 4.5 dBs, and then it goes up again. And if you look at this, the separable state I showed you before, like this independent spins, would have been the variance of square root n. This is 0 because it's in dB. This is this line here. So this would show, if you rotate this state, it would have no dependence, so it's a line. But what you see here is clearly dipped down, and that you can show that you have variance suppression here on the cost of increased variances here. Now, in order to make really a statement that this is a non-separable state, you have to measure another thing too, namely the coherence of the thing. But essentially, spin squeezing is an entanglement witness. Coherent spin squeezing is an entanglement witness, and showing you that you have in your system quantum resources. Okay, so this is, on the one side, something interesting if you want to show that you have entanglement. On the other hand, it shows you also how to use it. It's a difference, right? Because variance analysis allows you to subtract noise. If you do an interferometer, you are not allowed to subtract noise because you don't know what to subtract. It might be a signal you subtract. So this is a nice way. If it's Gaussian states, you can do all these tricks and get rid of technical noise by subtracting it if you understand it quite well. So now, if you have this, it says the phase estimation error is given by the squeezing factor over square root n. So it's a prefactor. So if you have more particles, then you would do better by this factor. In our case, it was this 5 dB, or about a factor of 4, which is 6 dB. Okay, so now if you think of our results, and experimental results was n equals 400, squeezing of 5 dB is not so overwhelming, because if you take 4,000 particles, which is trivial for these experiments, you're better off by classical measurements. Okay, so this was always a question. If n equals 4,000 classical, why bother? Okay, so now you can say, well, if I take n 4,000, I can just squeeze the 4,000 the same way as I did before. It turns out that this is not so easy, because if you take 4,000 particles in these blobs here, very concentrated, you will have them not for very long. They will disappear by three-body collisions. They will just form molecules and they are gone. So essentially, you are density limited in these systems. You cannot increase the density above a certain threshold. So that's easy. You just open up your trap, and you get the same density. Okay? If you do this experiment and you do the squeezing, you see this. So essentially, what you see is that this whole thing starts to separate and demixes. Okay? Now, with my simple explanation of spin degrees of freedom and motional degrees of freedom neglecting, this will not work, and the squeezing also does not work. Okay? So essentially, this kind of naive scaling up by just making the trap bigger and bigger, and you will go to the continuum limit, and you will not be in the single mode approximation to the squeezing well. Okay, now the solution to this problem is what the Roman Empire did, namely divide and conquer. You have this big system, and you want to control it, and what we can do, as I showed you, I can divide it into small parts. And the small parts I can control very well. I can do even deterministic squeezing. So if I start with the same condition on each of these blobs, they will squeeze the same way, because I start with the same initial condition. So essentially, you would say these 500 atoms is nice. We have here a little bit more than 6 dB squeezing, but I have more of them next to each other in one shot with the same technical noise. So now I can just ask, if I add them up, do I keep squeezing or not? And you do. You get about 5 dB squeezing for 12,000 atoms, because they are all squeezing the same way, if they are equally, if they're not too different in density. Okay? So in that respect, we have now the problem solved in the upscaling. I can now do 1 million, 2 million, 10 million, you name it. I just have to divide it. And if you do it in 3 dimensions, you have lots of possibilities of traps, to make small traps. So essentially, this squeezing will work also for large numbers. Now, for the detection, you would also ask, well, you know, I have this problem. If I want to detect the phase shift, okay, so essentially I want to measure this direction now, I have to produce the squeeze state. Okay, we can do this. We have to rotate it. Okay, and then actually I'm sensitive to what I wanted to be sensitive to, namely magnetic field difference, i.e. spin up has another energy than spin down. Now, there are 2 issues to it. The first issue is we are here in states which are first order magnetic insensitive. So on the second order. This is actually not what you do. I mean, if you want to measure something carefully, you take something which is very sensitive. Okay? This is a minor part, but we will solve that. The more critical part is, if you rotate this ellipse like this, the nonlinearity is still there. And now the nonlinearity is even larger, because you rotate it into the shear, and it will smear out faster. If it smears out faster, actually you lose all this nice phase sensitivity. Okay? The solution is squeezing swapping. So what you do is, you just swap this state down to this state here with a pi pulse. And if you do this, then you gain 2 things. First of all, you get first order sensitive, magnetic sensitive. And secondly, you get rid of all the interactions, more or less, because I said rubidium is so special that all the scattering lengths add up in the way that there's no linearity, vanishing linearity, very small linearity. So essentially now this is the way of doing magnetometry with this kind of squeezing of 6 dB. Then you characterize it, you find out there's a 3 dB useful squeezing, and then you do the experiment. So what you do is you take these clouds, and then you do a pi over 2 sequence, i.e. a Ramsey sequence. Okay? And you change the phase, and you get, on the left-hand side, you get a fringe. On the right-hand side, you get a fringe. And now if you look at this carefully, you see they are not the same. You can also take the difference, and then you see they're not the same. So essentially, these fringes have a phase shift to each other. And they have a phase shift to each other because the magnetic field here is different to here, because you have a small gradient. Okay? And this turns out to be about 20 picotesla per micrometer, just a number. This was the experimental setup. That's what it was. Now, one has to say here, the magnetic field might well do like this. You don't care because you analyze the differences between left and right. So you subtract these kind of big fluctuations. But the gradients, you cannot, they don't subtract, they add up. Okay? So at the end of the day, you can then ask, can I use these kind of blobs, squeezed blobs for gradiometry? And you can have different strategies, i.e. you take these single blobs here outside, they are squeezed, i.e. you're below this dashed line. This is standard quantum limit, and here below. Or you take this strategy, adding them up, and then essentially you become more sensitive, but again, the data points are below the dashed line, i.e. quantum enhanced. Now the question is, why do you want to be quantum enhanced? So now these detectors here are special in the sense of they are small in volume. And so now you can ask, what kind of detectors do exist for small volumes of magnetic fields? This is a peculiar situation. If you want to measure magnetic field very accurately, you would not take a small device, you would take a big cloud and measure Zeeman shifts. Yeah? But if you want to measure very close, then you want to have small parts. And if you compare the work what we have done here, this is the first result, just taking the system we have. Then it turns out if you take the probe volume and the magnetic field sensitivities, this first just proof of principle shows that this actually is already in the ballpark of other experiments. Now, if you do an improved work of that, you could now go down to here. And then essentially having the advantage that you can do gradiometry directly. Not that I want to go for this, but this is just showing this might be one route, which is maybe interesting. Okay, so now with that, I would like to go to the squeezing overall. There's lots of things happening. For many years, there's an archive paper now. It's a review article while Luca and Roman should get most of the credit, who did lots of the work, most of the work. And here we have metrological gain versus number of particles. And you see here 3 colors. And these are the ion traps. Small numbers, but almost Heisenberg limited. You see here the BEC experiments, which are in between. And the cold atoms with kind of the projective measurements now with light interaction. They were below this BEC experiments, but now they are far up here. I mean, there's even a twiddle line here. So this is amazing results of about 18 dB by James Thompson and Mark Kasevich. So essentially, this is a projective measurement. It's not a deterministic squeezing, but it's kind of conditional squeezing. So with that, how much time do I have? There's a clock. There. 10 minutes. I will need 10 minutes. Sorry. Okay. So this is squeezing. And you can see this bare eye in the experiment. This is experimental data with squeezed state, and you see the variance is smaller than the blue one, and with that you can do better measurements. Now we come to the question mark state. Okay, so now first of all, how do you produce a question mark state? And then the question is, can it do also better in interferometry? Now we have this Hamiltonian, and we switched this part off, but now we switch it on and leave it on, and we also kind of change the sign plus. The plus is important because now what follows with the plus is this here. The first thing is you have the shear, as I explained. Okay, so the further up you go, the faster it goes. Then you have the linear coupling, which is actually a rotation like this. So now you have to do the solution of this equation by aerobics. Namely, you have to do both motions at the same time, shearing and rotation. And it looks like this: shear, rotation, shear, rotation, shear, rotation. Okay? So you see what you do is you shear, you rotate into the shear, it gets faster sheared, you rotate in the shear, it gets faster sheared. So essentially it explodes in this direction. Okay? That's why we call this explosive squeezing, and that's why TNT squeezing. Also, it's also for twist and turn. And essentially it turns out that if you go to the classical limit, of this problem, you find out actually it's indeed you sit on an unstable fixed point and they exponentially explode from this fixed point. Yeah. And it's connected also to the phase transition properties of the transfer field Ising model. Okay, so without sound, but I hope impressive enough, it's like the explosion. So you start with a coherent state, you squeeze, and then essentially if you rotate first and further, the rotation takes over the shear, and then you rotate over the top. Okay, so now if you look at these dynamics here, then you see you naturally get squeezing, and then you get this S-shaped question mark state. Question mark state without S-shape, yeah, question mark state. And if you calculate this, you can do this, it's a very simple problem. You can calculate that the entanglement entropy increases monotonically. Okay, so you squeeze, go further, you get more and more of entanglement generated in this state. Up to, if you're at the very top, you will be almost a cat state. So reaching almost this Heisenberg scaling. So essentially it's worth going for these question mark states. Now, if you have this, do the experiment, then we have to think about how can we grasp what's happening in experiment. And what we do is we take these 40 experiments we have in parallel, then we apply this Hamiltonian, and then we do, after each realization, we do a small rotation and measure. A small rotation, measure, a small rotation, measure. So we do a kind of tomography, okay? Then we claim, and we don't claim, but what we do is we do a maximum likelihood reconstruction of the density matrix, which we know has to be wrong, because it's 300 particles, the density matrix has 90,000 inputs. Yeah? So 90,000 inputs measuring with an error bar which is small is hard, yeah? Lots of work. But we don't care about it, so we just do the maximum likelihood reconstruction, and then actually we represent this state on this generalized Bloch sphere. So essentially, we take this density matrix, we reconstruct it, and represent it in coherent states. So all these nice quantum features disappear anyway. And in chaos, this is called Hosimi function. So you average over this h bar, and then essentially all this vanishes, what's quantum, but the classical feature you get. Okay? And that's essentially what they plot here too. It's just a classical feature of this state, because you cannot represent the state on this sphere. It's just like a representation or qualitative representation. So you do this experiment and you see this. Now we come back to if it's bad or good. So what you have here is this is worth about 100,000 PCs, which is a large number for our community. But what you get for free now here the distributions of this spin vector on the sphere as a function of number of particles. And you clearly see that as you change the number of particles, you get this additional, I told you, this set component of this magnetic field. So essentially, this vector, the magnetic field goes from down up to the symmetric case, which is about here. Okay? So essentially, this was important because we wanted to show that this state has some resources, and for that you have to know approximately what it looks like. If you don't know how it looks like, it's very hard for the following. Okay, so we take now 380 particles as the right number and do all the analysis on this number. Okay, we have the others too, but this is just what we do now in the following. So now we have this state produced, we put it in an interferometer, okay, then you would say, well, if the interferometer rotates in this direction, take this banana in like this direction, this is a bad idea. So the best thing is first rotate it such that the variance is minimal. Okay, it's not shot noise, it's above shot noise, but it's minimal, and then you rotate. And then you ask, how well can you estimate the angle? Okay, and you would say no squeezing, no gain. We just stop it. But this is just the variance analysis. So essentially what you should do is just ask the question, given these two phases you adjusted, how different are the distribution functions you get? And then you can ask, well, is there a measure for differences of these functions? And there is one which is called Hellinger distance, which is actually very interesting because it looks very familiar to us. So it's just there's a classical distribution function, natural numbers. So numbers, not complex numbers. Take the square root of it, take the difference, okay, square it and sum it. Looks very much like taking psi and psi, square it and sum it. This has a name, it's Hellinger distance, and this you can measure because you can measure the distribution functions. Okay, this is an observable. Now the question is, what's the connection to the Fisher information? Is there a connection to the Fisher information? Well, somehow it is, because it says, well, how does the distance increase as a function of your small parameter phi? If it increases fast, then it's very quickly distinguishable. So there is a connection, and it turns out there is. The Fisher information I introduced here, and it turns out this Hellinger distance, the phase dependence on it, is quadratic close by, and the prefactor is the Fisher information, i.e. the curvature of this distance is the Fisher information. If the Fisher information is high, it means it changes very fast in distance. And that makes it so nice to detect because it's actually very sensitive to your parameter phi you want to estimate. Okay, so now you can measure it. You take the distribution functions and you measure it. This is actually a little bit heavy. You have to do lots of statistics. And you have to know relatively well at what angle you have to rotate. And that's why you have to do the measurement first. If you find the right angle, this is not true for every angle. It's only a very fine-tuned angle where you can find this feature. That if you take the Hellinger distance, you calculate this, and take a parabolic fit, you find out this curvature actually is 1.5 and it's not 1. So it's bigger than 1. That means there is quantum resource in there. It changes faster than classical possible. Okay? So now if you have this, you can do this a little bit more systematic. Finding this is not simple, yeah? Because you have to find the first angle right. The first rotation here I made just quick. I said this is easy. But this you have to find. So now you can do this systematically. You can ask, well, I start with a coherent state, you go to a squeeze state, you go to this banana state. And now you ask, what's the Fisher information here? Okay, if you do this experiment for this kind of squeeze state, you find out the Fisher information you extract, i.e. this curvature, are the red points. And you can compare this to the squeezing directly. And in the case where you have Gaussian states, those two things coincide. Actually, the angle where they happen to be the best, as well as the value, is the same. So the Fisher information maps onto the squeezing parameter if you have Gaussian states. If you now go further and you lose the squeezing, as you can see, so the variance, this minimal variance is here. But you see the Fisher information does not vanish, but it stays there. Okay, it's another angle, but it stays there. Now you would say this is nice, maybe. Yeah, well, I like it. Yeah. It's very general. There is no assumption about theory. I just take measurement results and look at the reaction of my system. And I can show from that there is quantum entanglement in there. That's actually a very strong statement. The other thing you might say, well, from metrological points of view, you told us that actually this Fisher information, this squeeze state, this over-squeeze state is better than your squeeze state. But where is it here? The Fisher information here is smaller than here, so better take a squeeze state. Okay? And it turns out that actually what you measured was classical distribution functions. So everything is in there, all the noise you have, and also your incompetence in making a good detector, i.e. counting detector. So essentially, that this does not go up here, and that theoretically goes up if you have no noise sources in your system. But if you have the noise source, this actually will kill you at the very end, and that's why we could not go further, because our detector had this ±4 particles error and noise, and that reduces also this classical distribution functions are convoluted by this resolution. And that's why you can just show it the transient that you can detect it. But in principle, this is a very general way of detecting entanglement, i.e. the response of a system to small rotations, to small unitary transformations. Okay, so in order to heal this kind of problem of detector, we went for this based sensing on time reversal. Namely, if you can entangle and disentangle your system, then you can get rid of these constraints that you have to be able to detect this entangled state in here. And in order to do back and forwards running in time, we had to choose a system which is different to what I showed you. And we take spin-changing collisions, where Paul is an expert in here. You produce pairs. And the good thing about the Hamiltonian is that if this is here macroscopically occupied by a condensate, then I can reverse the sign of this part here by just reversing the sign or do a pi phase shift, reverse the sign of the field. And with that, you can run back and forwards, and that is actually then allowed us to demonstrate the SU11 interferometer. This was discussed 30 years ago in optics, and now we put this in the context of this back and forwards running in time, and we could show that you can do quantum limited interferometry. And if you look at this fringe, it's very interesting because that's the fringe, that's the mean. And you have noise like hell. And you can ask, where is the best working point for this interferometer? And it turns out to be here, at the zero crossing. So at the 0 point, you have the maximum sensitivity. This was well discussed 30 years ago. Okay, with that, I'm at the end. I showed you what we did over the last years on quantum metrological aspects with BECs. The recent thing, hopefully it comes out today, is about the observation of phononic lamp shifts by looking at immersed systems, i.e. fermion immersed in a Bose field. We did some work on chaos, emerging chaos in many particle systems by showing Poincaré-Birkhoff's scenario. And we have done observed universal scale or scaling behavior in the dynamics of strongly quenched BECs, quantum gases, two-component bond quantum gases. And this is actually a route I want to pursue further and also look for entanglement generation in these extended systems. And with that, I thank you for your attention.